This lecture presents an introduction to the capabilities of the program Mathematica, a general-purpose program for doing both analytical and numerical calculations. We're looking at a Mathematica document called a notebook. Here at the top are some links to web pages at the developer of Mathematica, Wolfram Research, giving some other very introductory information about how to use Mathematica. Let me begin by giving some examples of the capabilities of Mathematica just to illustrate the breadth of its abilities. So for example, Mathematica knows calculus. So you can type formulas like e to the I pi plus 1, and it knows how to evaluate that as 0. You can expand functions in Taylor series. In this case, expanding e to the x about the point 0 out to, say, 4 terms. And it's able to do that expansion quite nicely. It can do integrals. It can do indefinite integrals, that is, integrals without the limits. And it can also do definite integrals. It can take derivatives, so it can take the derivative of this function that we've just integrated and get back log x. It can do numerical integrals for functions that can't be integrated analytically. So for example, e to the minus x cubed can't be integrated in closed form, but it can provide a numerical answer for a definite integral. Mathematica can plot functions. In fact, it has many plotting capabilities, but the most elementary of them is just simply to plot a single function, in this case, say x squared, for x ranging from 0 to 10. And I'll pretty this up a bit by putting a frame around it. And give myself some frame labels. It can make tables of numbers in a variety of ways. The simplest way is with tables. So for example, I can make a table of the squares of the integers, the values of the integers and their squares for n ranging from 0 to 20. Sorry, I want that to be 0 to 10 to match the plot above. And I can plot data points like these ones that I've just created by using list plot. Finally, I can combine two plots, for example, to put this curve in the same plot as the data by using show. And we can see that the function obviously describes the data. Mathematica in general gives exact results to any expression that it can. So for example, sine pi over 3 can be given in terms of an analytical expression, square root of 3 over 2. If you want a number, instead, you can wrap the function n, which you can think of as numericize around that. The percent sign refers to the last output, that is this thing here, so n of percent gives the number 0.866. So Mathematica should be thought of as a language with a pretty big vocabulary, but like an ordinary natural language, you don't need to know so many words to say a lot. Mathematica is what computer scientists would call a high-level language, meaning you can do a lot with a single function, and the functions can work on big objects like lists or vectors or matrices or things, not just individual numbers. And that makes it easy to write a program or a function that does a lot with a very few lines. As I've illustrated, Mathematica can do both analytical and numerical type calculations, and what I haven't shown you yet is that you can define new functions which can do tasks that Mathematica hasn't been designed to do out of the box. In the examples I've shown, maybe you're beginning to notice some of the features of the grammar of Mathematica, the rules of input. So for instance, you'll notice that functions take their arguments in square brackets. It's n of percent with square brackets around it. It's sine of pi over 3 with square brackets around it. And that the built-in functions are, well, almost without exception, capitalized English words or such words strung together. Words like show or list plot. And again, here's list plot with its arguments in square brackets. Here's table, a capitalized English word. The arguments of table come in square brackets. N integrate is perhaps an exception, but the N stands for numericize. So that's basically strung together words. D is a typical symbol for differentiation in calculus, so it doesn't write out derivative, which it could have used. Integrate, okay. So you get the idea. The functions have names that are not obscure. The function arguments, as I've said, are in square brackets. Curly brackets, which we've encountered several times, are used for lists of things. For example, the arguments to table, where I said, well, it's a table in which n ranges from 0 to 10, that specification comes in this little list here. This table is producing a list of pairs, and here's the prescription for the pair that it's supposed to produce, n comma n squared. And here's the output, okay, which is in fact a list of pairs. And so the outer list is this curly bracket right here, and its mate, which lights up nicely in green. And the first element of that is a pair, which is itself a list of two things, and the next element and the next and so on. It's all lists of pairs. So many objects, vectors, matrices, lists of options, things like that are all demarcated with curly brackets. Parentheses are used for grouping, as in algebraic grouping. So I don't think we've used any parentheses yet, but if you wanted to say, a plus b all squared, you'd use parentheses for that. Double square brackets, which we haven't yet encountered, are for picking off the elements of a list, sort of like a vector index. Space is for multiply. So when we wrote up at the top here, e to the I pi, that's exponential of I times pi, but there's just a space, no little star there. When we wrote x log x, that's x space log x, no little star. It's meant to be easier to read. If you leave the space out, it will think you're talking about some function xlog or some variable ippy. And so the space is important. If you want to show multiply, you need the space. Finally, what you haven't seen me doing, but I've done every time I executed a line of input after I've typed it, you use Shift-Enter to evaluate a line once you've done it, once you've got it typed in. And if I want to re-evaluate a line, I just click in on the line, and hit Shift Enter, and it reevaluates it, which allows me to change what I've done if I didn't quite like it, and type it and execute it again. I could also highlight the cell over here and Shift Enter, and that will have the same effect. So I've just now mentioned cells. The notebook is made up of cells. Everything bracketed by one of these little skinny blue-gray lines on the right is a cell. So there's different kinds of cells. This is a section head cell right here. Up at the top, this is a title cell. This is a text cell. It's just a text label. This is an input cell. This is an output cell. And you notice that cells are grouped. So the input cell is grouped with its output cell, and everything under a section heading is grouped together, and everything in the entire document is grouped together like so. So what is the purpose of this grouping? Well, if I take this group right here and I double click it, it folds up, it disappears. You can see the little arrowhead on the bottom is an indication that there's something in there, which if I double click again, it comes back. And that is a way of organizing the document and hiding stuff you don't currently want to see. Any cell that groups things can be double clicked like that to hide its contents, like this. You can use this to hide the output of a command if the output is long, for example. The text cells, of which these are examples here, are good for making comments as you go along. And so one of the nice things about a Mathematica document is the ease with which you can introduce headings like this and text cells like that makes it easy to document, to comment on the work that you've done so that someone else looking at it or you looking at it sometime later can understand what you did. So that's some examples of what text cells and section head cells and so forth are good for, but then the question is, how do you put them in your document? So if you want to put, for example, a new section here, then you move the cursor up and down until it becomes horizontal and click in, and it makes this horizontal line, and that's where new input will appear. And then if you want to make a heading, you can choose the format style section, which is what we are looking at here when we see working with cells. That's a section header. There's a whole hierarchy of these. But if you choose section and then start typing, you get a matching section head, matching in the font and also matching in its nesting hierarchy over here. So now things I type below here will nest underneath this, just the way that the cells under here nest under the section head working with cells. So for instance, I can add a text cell now, which is style text, and then I can type a new comment. There are shortcuts for these cell types, which you can see over on the right here. A section is Command 4, text is Command 7, and input, which is the default without doing anything, is Command 9. So if I want another text cell, I can just Command 7 and make another comment, and so forth. You can work with cells using copy and paste. So for example, if I copy this in the usual way, Command C, and then I click here and make a horizontal line, so I've moved the cursor someplace in between cells, and you see it turns horizontal, and then if I click in there, I'm ready to paste in that point. If I do that, I get a copy of that cell, obviously. If I click on this and just delete it, it goes away again. One final thing to note about input and output cells is they get labels telling you what number they were in the sequence of things that were executed. So this was the 15th input and the 15th output. If you type an input cell but you haven't yet executed it, it doesn't have a little label for input. Once I execute it with Shift Enter, then I get an input and an output label. So we have used a couple of times, though you may not have noticed it, variables and assignments. So when you want to store a value, you store it inside a variable. So where did we do that? Well, we stored those plots actually in a variable that we called plot2 and an earlier plot1. So this variable actually stores an entire plot. And later we used the fact that it was stored because we said show plot1, plot2. So a variable can store basically anything. The variables in Mathematica don't have a type. You don't have to say, oh, this is a real variable, this is complex, this is an integer, this is a vector, this is a matrix, this is a 3 by 3 matrix. Variables in Mathematica are typeless, which means you can store anything in them just by setting them equal to something. So for example, I can say a equals 1 plus x to the 4th and Shift Enter, and it says fine. A is now 1 plus x to the 4th. And if you want to know what a is later, you can just type a and Shift Enter and it will echo 1 plus x to the 4th. Or if I say a squared later, it knows what a was and it squares it. You can reassign a variable. Its value is not permanent. If I say a equals 1 plus y cubed, well, I changed it. Now a is 1 plus y cubed. And furthermore, if I say y equals 2 now, and ask about a again, it knows that y is 1 plus 2 cubed, or 27. Now, this is a great virtue, being able to reassign variables, because you can fix mistakes and change things and so on. But you can get confused about what the current definition is if you don't remember what you did last. And the notebook is not like a paper tape coming out of an old-fashioned office calculator. You can't look back at the notebook and see the sequence of calculations. So being able to do things over again is a great virtue because you can experiment and fix mistakes, but you can get confused about what the state of a variable is, which is why if you want to just know the value, you can simply Shift Enter the variable itself and it will echo the value. Sometimes you need to clear definitions from a variable, and so for that purpose there's a function called clear, and that removes all definitions from the variable. One thing you'll notice is that when I cleared a, it turned from black to blue. If I give a definition, it will turn black, and everywhere in the notebook it turns black. If I clear it, it turns blue. So blue is a visual cue that the variable doesn't have a definition. This is useful in many respects. For example, if I'm trying to type sine pi over 3, but I typed sync instead, then sync is blue. It doesn't know this function. Sine, it knows just fine, that's black. And so that's a clue that you've made a typo. So vectors and matrices in Mathematica are handled in terms of lists. And we talked about lists before as being demarcated by curly brackets. So for example, if I want to define a vector or a list and I want to save it in a variable called b, whoops, I typed into the wrong place, B, then I say B equals whatever I want my list to be, 5, 10, 15. And this maybe could be interpreted as a three-dimensional vector, or maybe just a list of three numbers. And if I shift enter that, it echoes the current value of B. I mentioned before the double square brackets, which are how you access the elements of a list. So B, the second element, is 10. And notice when I type those square brackets that they light up as sort of cyan colored when they have not yet been matched. And when they get a mate, they blink and turn black, and then this blinks. And that helps you know that you've matched the brackets in an expression. And square brackets match with square, and curly with curly, and paren with paren. And you'll see that when you enter things. Similar to vectors, a matrix is written with curly brackets and lists, and it is a list of its rows. So, for example, 1, 2, 3, 2, 3, 4, 4, 5, 9. And you see how the curly brackets match up as I close the expression. So there's a 3 by 3 matrix. Operations like matrix multiplication and matrix inverse and so on can be done on the entire matrix at a time. So for example, C dot B is multiplying the matrix C times the vector B, or C dot C is multiplying the matrix C times the matrix C, or I can take the inverse of C like so. So as I've shown you before, there are some visual cues that come as you type, and those are useful to note. Undefined variables are blue, defined variables are black, unmatched delimiters are cyan, and when they match they flash and turn black. So with any complicated program, it's helpful to have places to get help. Mathematica provides several. One thing is if you start typing a command, then you will get some suggestions about how to complete that command, and that can save typing if you just click on one of those. So if you start typing in, it helpfully suggests integrate and other such things. If you make a typo that doesn't correspond to anything, then you don't get any suggestions. Another thing that you can do to get help with a command is question mark the command. So you know that there's plot, but you don't know how to use it. So you type question mark plot, and then you get a brief summary of how you use it. Plot a function, and then the range x min x max generates a plot of f, etc. And these can be a little bit terse, and if you want more of an example, you click on this little greater, and that will bring up a help page which has a lot of information, as including, most importantly, examples of how to use the function. This facility here is basically opening up the Wolfram documentation, which you can get at from the help menu right here. And you can search in here fairly effectively. So for example, if you say plotting and hit return, then you get not only information about the function plot, but a little tutorial about basic plotting, about plotting options, if you want to plot a list of data, so there are lots of possible tutorial topics on plotting. So the help is actually fairly decent. in Mathematica. So one thing we haven't done yet, but which does figure importantly in more sophisticated uses of Mathematica, is to define our own functions. So I'm only going to give a fairly trivial example of that right now. So if you wanted, for some convenience, to define a function f of x, which was a particular polynomial, then you could just do it by typing in the recipe for the function. And what you've done here is given the function a name f. Because it's a function, it takes its arguments in curly brackets. This special syntax here of x with an underscore after it means an argument of the function which for the purposes of this definition is called x. An argument here called x. And then here is the definition of x. This funny looking not quite equals sign, colon equals, is a delayed assignment. In other words, don't stuff this right-hand side into f right now, but save this as a recipe so that the next time I ask you, you follow this recipe in computing f. So I want to keep this introduction short, so I won't go more into defining functions and so forth, but for completeness I do want to say that there are three kinds of equal signs that appear, or equal-ish looking signs that occur in Mathematica that are not the same. One of which is the equals that we encountered, which does not mean two things are equal. It means make these two things equal. It's what computer scientists call immediate assignment. Do this right now. It's what we did when we used the variable b, for example, and set it equal to this list. Do that right now and b will immediately be this list. This colon equals is delayed assignment. As I said, this is a recipe you should follow if I ever ask you to evaluate the function x, but don't do this right now. The third kind of equal-ish looking symbol is double equals, equal, equal, and that is how you write equations in Mathematica. So for example, if you want to solve, as Mathematica can do, the quadratic equation analytically, then you need to type equal equals right here. And Mathematica immediately converted that into that little double equally looking symbol. But what I typed was equal equal and then 0, comma, I'm solving for this, solving for x. You'll notice that b and c here are black, and because I wanted this to be a solution for just the algebraic answer without any definition of b and c for the quadratic formula, I want to clear b and c before I do this. And this is a little pitfall in Mathematica. If you've used a variable for something and it's got some value in it and then you go using it for something else, you can sometimes get weird results. So in this case I clear it, that turns b and c blue, and now I know these are just letters as far as Mathematica is concerned. They have no meaning. And so when you do the solution with solve algebraically, you get the two roots of the quadratic equation.